Yeah, my plan for today is to continue the torsion we started last week, okay? Because we need to have torsion before we talk about idealized structures, which is something we at least are going to start today. So basically, I will show you how we can build this simplified model. We can see this figure here, this big figure here. So we are going to talk about this. So basically, how can we move from a full effective cross-section to an idealized cross-section? Very simple. So we're going to do a lot of simplifications. For example, that the string or stiffener that you have there. Or for example, this skin here. Usually the stress state that you have installed is a direct stress and the shear stress. So you have the stiffener here with a direct stress, carrying a direct stress. So what we are going to do is we are going to build an idealized or a simple model where you have the skin carrying only shear stresses, and where you have what we call a boom. We call this a boom with circular cross-section, and this boom, it carries only direct stresses. So basically we have these two structural elements that they have a very different kind of behavior. So the boom, they carry direct stresses from bending, so they carry the bending loading, while the skin, they carry the transverse shear or shear flows, okay? So this is very different than the real structure where the direct stresses and the shear stresses, they are all combined in this model. And also, another simplification is on the geometry, right? So this cross-section here, idealized cross-section, you have only a skin which we assume to have zero thickness, and you have a boom with a circular cross-section, so you only need to know the area of this boom. While in the real structure, you can have much more complex. You can have, this stiffener with this Z shape, right? The Z shape geometry. You can have the skin with different thicknesses. So this can become very complex in a wing, in aircraft, right? So what we are going to learn is how can we build this idealized model from the real model. So basically, how can we calculate the area of this boom so that these two models are equivalent? Okay, that's what we are going to do. But before we do that, we need to discuss a bit on torsion. We need to continue the analysis. So last week, basically, I show you that in torsion we derive it. So imagine if you have a tubular cross-section like this, I show you that the shear flow around this cross-section is constant, right? And then if you have a torque applied on this cross-section, we concluded last week that that torque is 2QA. Remember where this A is the area of the cross-section, right? Remember this? Even I gave you an example where you knew the torque, and then I asked you to calculate the shear flow. So basically we only had to do this to calculate the shear flow, quite simple. But this is not enough. We need something more for torsion, because this is a closed cross-section, a very simple cross-section, but we can have, for example, in a wing, we can have cross-sections like this, where you have multiple cells. You have one cell here, you have another cell here, right? And another cell here. So we need something more if we want to solve problems like a wing in torsion like this. And that's something more we need to have is basically the twisting angle of the cross-section. Why do we need to have that? For example, because we cannot allow the wing to twist something like this. Right? So these three different cells that you have here, for example, this cell 1 cannot rotate like this, and this cell 2 rotate like this, and this cell 3 rotate like this, right? They need to rotate by the same amount. If this happens in a real aircraft, the aerodynamic disappears, right? So that's also why we need to derive something more for torsion, okay? And so in order to start that analysis, or to continue that analysis, I'm just going to copy this one here, and this one as well. Okay, so we are going to focus again on this, this element here. Okay, so this element I'm zooming in this picture there. So what is going to happen is this element will have a shear flow, this one flowing, right, in all these directions. You see, in this element, okay? This shear comes from the torque that is being applied on the cross section. And what we are going to do is we are going to use calculate the energy, or the contribution to the energy that this small element that is in torsion, what is the amount of energy this element is generating when it is in torsion, okay? And in order to do that, the expression we are going to use, so basically this is our initial configuration, okay? This one in red, and this one in green is going to be the final configuration after torsion. So this element will distort, right? Torsion is a kind of a distortion, right? And that distortion is being given by this angle gamma that you see there, okay? So one thing you need to consider is this gamma is a very small angle. We are in a linear elastic domain where these deformations are very, very, very small, okay? So it's a very small distortion. So if we, in order to get the energy, so you know that if you have here displacement force, when you start to increase the force, you start to have an increase in the displacement. So the energy basically is the area below this curve, right? So basically is 1/2 the force times displacement, right? You agree? Is the area of this triangle, right? That gives me the energy. So what is the force we need to consider? Well, the force we need to consider is the force here in this point of this element. So this is a shear stress. Okay? So we know the shear stress. So this is a shear flow, shear flow. We know the shear flow is a force per unit length. So if I want to get the force, I need to multiply this shear flow by the length where the shear flow is acting in, and that length is ds. You all agree with me? So qds will give me, basically will give me the force that I'm looking for, qds. So this is the force, okay? Now this point in this element moved from this position to this position, right? So basically it moved by this L gamma. How can you calculate this L gamma? Well, you have here this rectangular triangle. I'm going to draw here maybe in blue. Okay? You see? This rectangular triangle you have here in blue. So this is L. This dimension is L. So tangent of gamma is going to be this height, let's say this height h over L. So we are looking for, sorry, not h. Let me use, to be consistent what we are doing, let me use d, this d here, okay? So tangent is going to be d over L. So if we calculate this for d, we get this is L tangent of gamma. Because this angle gamma is very, very small, linear elastic, small deformations, we can say this is approximately equal to L gamma, okay? So this error becomes higher if we are applying a very large torque, for example, so that this distortion is very large. So in that case, this approximation is not very accurate. But the thing is that we don't want, for example, if you think on a wing, we don't want this distortion angle to be too much, right? So very, very small. Otherwise, we are affecting the aerodynamic performance of the aircraft. So we are usually dealing with very small values of gamma, so this tangent of gamma can be replaced by gamma, right? And so we can say that this D is L gamma, so we can multiply now, we need to multiply by D, which is L gamma. So this gives me the contribution for the energy from this element of my tube, right? Now, what can we do now from this? So let's find some space here. So there are some things more we can do to simplify this analysis. One is the shear flow is equal to the shear stress times the thickness, right? Don't forget, the shear stress is a force per unit area. The shear flow is a force per unit length. So if I multiply the shear stress by a length, let's say in this case the thickness, I get the shear flow. Another thing we know is from Hooke's law, right? We know that the shear stress is equal to the modulus of rigidity times the shear strain. And the shear strain is this gamma that this distortion angle gamma is our shear strain, right? So, conclusion from these equations is we can say the shear strain is shear stress over the modulus of rigidity. This modulus of rigidity is basically the stiffness of the element to shear, right? It's a distortional stiffness, let's say. And then if I replace the shear stress from this equation, which is Q over T, I get this is going to be equal to this, right? You all agree with me? Now, what can I do from this? I can take this expression for the shear strain and replace here where I have this gamma. So if I do that, I will get my contribution to the energy to be equal to Q ds L Q over GT, right? Or I can write this in a different way. I can write, so let me continue here now. I can say that the contribution for the energy is going to be equal to Q square L GT ds, right? Oh, I think the 2 is missing here, right? Yeah, 1 over 2. Okay, so this is the contribution of that element, this element here, on the 2, but the thing is that we need to have the total energy. So we need to basically integrate this. So if I want to have the total energy, so it means I need to do the integral of this equation, right? Agree? So if I do the integral of dW, what I get is W, the total energy. And then this is going to be the contour integral, right? Is it the integral in this? Don't forget, we are integrating on this S variable. I think it's here, yes. This S variable is the variable along the skin of the cross section, right? Agree? So we have something like this. Okay? So we need to keep this expression. In fact, there's something more we also can do, which is we can use this expression here, which relates the torque in torsion with the shear flow, Q. And we can replace in this equation. So basically what I'm saying is you have this expression that relates the torque with the shear flow. I can replace in this equation, and I can write the You agree with this? Huh? So I'm just replacing this expression for the shear flow. In that equation, I have shear flow squared, right? I replace there, and then I get dA should be squared, right? dA should be squared. Is this? Yeah.
Yeah. You repeat what you meant with the integral with the circle.
Yeah. So here, when you integrate here, you want to get the total energy, right? So on the left-hand side, you have the integral on dW. So that will give you the W. On the right-hand side, when you also, if you integrate the left-hand side, you need to integrate the right-hand side, right? And the right-hand side, the integral is on this variable, ds. Now you need to see this variable ds, what it represents, right? You remember last week when we talked about transverse shear, right? We'd find this local variable ds that goes from the free edge on the cross-section, right? Here is the same in torsion. This variable ds starts at some point here, and then it runs along this contour, right? That's what this integral means, on the contour of the cross-section. In this case, this is a circular cross-section, so this s variable goes from 0 to 2 pi r, where r is the radius of the circle of the cross-section, right? Right. So another thing, so we also can keep this expression, not this, because one important thing is that you have the torque square, but the torque in the cross-section is constant, so we apply a constant in torque in the cross-section, right? So basically we can send the torque outside of the integral, so we can write this expression for, we can send torque, we can send G, we can send A, we can send this these three guys outside, right? So we can say we'll have T squared, we can send 8 as well, of course, 8G A squared, and then contour integral of L over T ds. Okay? We can keep also this expression. All right, so we didn't, this is not finished yet because we, let me shrink this a little bit, because there's still one thing that we need to do. We don't know how much is the total energy, right? This W, we don't know the value, we don't know the value of this W. But what we do know is, so this energy that you have here, is the internal energy, is the energy that is being produced by the internal shear flow. Okay? And we know that I think you did that in year 2, eventually, in solid body mechanics. This internal energy, so we can write this way, internal energy needs to be equal to the energy produced by the external forces. Okay? External forces or external moments. In this case, in torsion, in fact, is external moments. So the energy produced by the external moment is given by 1 over 2 the torque times the why is there so many spiders here? Yeah, I hate spiders. Okay, 1/2 torque times the twisting angle, theta. I'm writing theta, not gamma now, because I want to distinguish. This gamma here is a shear strain, right? I want to distinguish the twisting angle from the shear strain. So this is the energy produced by the external moment, which is the torque. And this needs to be equal to the internal energy, which is this one here, t square of 8ga square. Okay? You did energy methods in year 2, right? With Julia Alfano. I'm quite sure you did. No? Anyway, from energy balance, what this is saying is that when you apply, in this case, a torque, which is an external load, right? This torque will induce internal shear flows. So the energy produced by a torque needs to be in balance with the internal energy produced by those shear flows inside. So that's basically what we are saying here now, okay? So there's one more thing we can do. We can simplify this a lot. We can cancel this with this and make it 4 here, right? We can cancel the torque here with the square. So we can send this L outside because it's constant in the integral as well. And then we can say theta over L, right? If I send the L to the left-hand side, it goes to the denominator. It's going to be equal to the torque times 4ga square ds over t, right? Okay? Right? So this expression now will have a lot of, it will be very important for us. Why? Because what you have here on the left-hand side, this theta over L, basically is the gradient of twist, is the twist angle per unit length of the tube. Don't forget this L is this dimension, right? So basically, imagine if this distorts by this angle theta, what I'm saying, this theta over L, or this twist angle per unit length of my tube is given by this expression here. So we need to know the torque. This is a material property. The model of rigidity is a material property. You know which material you are using, so you know this G. This A is the area of the cross section, this area here, right? You also know this A because the geometry is given to you. This is the thickness of the walls. You just need to do this contour integral, then you can calculate this. We are going to do some examples today, don't worry, okay? You can calculate this angle theta, or theta over L. And why is this important? Because this is very important because now you can say, in this example here, for example, if this is your cell 1, if this is my cell 2, this is my cell 3, for example, I can say theta over L for cell 1 needs to be equal to theta over L for cell 2, needs to be equal to theta over L for cell 3. So that this does not happen, right? All these 3 cells, they need to rotate by the same amount. Okay? And then we are going to use these equations a lot when we work these multicellular cross sections like you have in a wing, for example. All right, so before we finish this part and do some application examples of this, I can just do one more thing, which is if I replace again torque by 2QA, again by the same expression, I can also write this. So if I replace these two, I can get the gradient of twist, or theta over L, equal to 1 over 2GA. Okay? In fact, this is the expression we are going to use more. So I sent the Q inside now the integral, because when we are working with the torque is constant. For if you have a multicellular cross-section, the torque is constant, can be outside. But if you have a multicellular cross-section, the shear flow for the different cells can be different. That's why I had to move it inside the integral, contour integral, okay? It cannot be sent outside the integral. And this expression is, in fact, the expression we are going to use a lot. So I can start with a simple example. We can start with a very simple example. I'm going to copy here. So this simple example is something like this. A rectangular cross-section, like this one. This thickness here is 3.0. This one is 1.0. So dimensions in millimeters, okay? The thickness of this wall is 2.0, and this wall here is 1.0. Now you need so from here to here, (300 millimeters), and from here to here you have 100 millimeters, okay? All right? And the question, okay, you have a single cell closed to cross-section, blah, blah, blah. You have an applied torque of 10, so the torque is 10 kilonewton meters. What they want is calculate the twist. So they have twist angle of a 2 meter length of 2, okay? And they give you the material properties, so the model of rigidity is 28 gigapascal. Okay? So the expression we need to use, so we need to use this expression we just derived, 1 over 2 GA. This, or we can also use this one here involving the torque. Right? This one here. Okay? So you can use any of these two. I think this one might be easier for this example because the torque is given to us, right? 10 kilonewton meter. So we have what do we have here? We have the torque is given. G is a material property, is also given to us. This A is very easy. Is the area of this rectangle. Basically, it's 300 times 100. We also have that. We have the thickness of these four walls. We have everything. So the thing we need to focus is on this contour integral. I can show you how you can do this contour integral. Okay? So let's do that. So theta over L is going to be equal, so the torque, 10 kilonewtons meter. So we have the option to work in millimeters or in meters. So if we work in meters, so I'm going to convert the torque from kilonewton to newton. So I need to multiply by 10 times 3, and I'm working in meters in that case, right? Now G, 28 gigapascal. So if I'm working with meters and newtons, I need to work with Pascal. So 28 gigapascal. So I need to put here 28 times 10 power 9 to convert gigapascal to Pascal, right? Now the area square. So I need to the area, sorry, I was just, the area square, so I need to convert this 300 and 102 from millimeters to meters, so I have 0.3 times 0.1, and I need to square this because I need to have the area square, right? Okay, so this is done, so let's do now the contour integral. Contour integral is not difficult. I know you guys, contour integral is already boring for you guys, right? Contour integral is even more boring, I know that. But don't worry, because, look, what we are going to do is we are going to run these four walls, and we are going to add the contribution of these four walls to this contour integral, okay? So, for example, if we start with this wall here at the bottom, okay, this one here, what I need to have is this ds basically is the length of the wall, okay, which is 0.3, sorry, we are working with meters. So I will put here 0.3, and I need to divide this now by the thickness of this wall, which is 2.0 millimeters, or we need to convert to meters. 0.002 meters, right? So this is the contribution from this wall here at the bottom. Now I need to follow the contour of my cross section. Now this wall in green. So I need to add the contribution of this wall in green. The length of this wall in green is 0.1. The thickness is 0.001. You see? And then I go to this wall on the top in blue. I need to add that contribution. The length is again 0.3. The thickness is 0.003. I'm going to continue here. And the last one I need to consider is this wall here, right? Now in black. The length is 0.1. The thickness is 0.001. That's it. If I add these contributions, I'm doing the contour integral. Make sense or not? It's not difficult, right? And then if you do all of these calculations, you should get this result that I have here, which is 44.64 times 10 minus 3 radians per meter. Okay? As you can see, this is a very small number, right? Very small number. Okay? Now, well, I think, did we answer the question or not? No, they want a twist angle. So this is not a twist angle. This is a twist angle per unit length. So if I want the twist angle at a 2 meter length, what I have to do is I need to multiply this. So let me copy. Okay. So this is my theta over L. So if I want my angle for a L equal to 2 meters, I just need to multiply this 44.64 by 2 meters, right? Then I get the angle of, well, this should be how much? 0.0892 radians. A very small angle, right? You see? That's how much this cross-section twisted. Okay? Does it make sense or not? Let's do one more now with multiple cells. This can be a bit tricky. That's why I want to do this with you, okay? Any questions in this example? Can we move? Yeah?
Can you go to the final solution, please?
The final solution. This one here. You guys have been, the video lectures in Panopto. It's working fine? Yeah, so I will upload this, okay? Panopto. Don't need to be copying. All right, so let's do now this example. So this one, you have basically is a 3-cell example. So the thickness here is equal to this in this wall. Same thing here. This wall, the thickness is different, is 4/10(3). This wall, it is 2/10(3). And okay. Yeah, then from symmetry. Okay. So this so you have here this symmetry axis and this symmetry axis of cross section. So the other thickness on the other walls, they come from symmetry, okay? This is a symmetric cross section. Now what do you need more? You need dimensions. So from here to here, this is 0.2. From here to here is 0.4. And from here to here is 0.2 as well, from symmetry as well, right? And then you need this dimension here, which is 0.2. Okay? And then you have this torque applied on this cross section, this torque which is equal to 10⁴ Newton meters. Yeah. Okay? So let me just see the question. What you have? Evaluate the shear flow. So what they want from this question is shear flows on the walls, gradient of twist of the entire cross section. Yeah.
So OT is in millimeters.
Sorry?
All the measurements in millimeters.
Maybe not. I think they are in meters. Okay? Yeah, in meters. Yeah, shear flows, gradient of twist. Yeah, that's what I want you guys to do. Oh, and there's one thing that is also given is the model of rigidity, 28 gigapascal again. Okay? For the entire, so all these three cells have the same model of rigidity. Okay? Now, I just really want you, so let me see. I want you guys to be aware that you will have here three cells. This is, let's say this is cell number 1. Okay, are you seeing? So let's say this is cell number 1. Then you have this cell here in the middle, which we say cell number 2. And then you have this cell here, cell number 3, okay? All right? And one important thing you guys need to be aware of in this kind of multicellular problems is that each cell will have a different shear flow. So let's say for cell number 1, so let me just try. Yeah, for cell number 1, you will have a shear flowing in this, let's say, anti-clockwise direction. Let's call this shear flow Q1. In this cell number 2, you will have a shear flow Q2. And in this cell number 3, you will have a shear flow Q3, okay? All right? So this is one first thing that is different when we are doing multiple cells from a single cell, which is each cell will have its own shear flowing in that cell, okay? Now, why am I doing this? Because, don't forget, we need to have the shear flows in each wall of this cross-section. So I'm just going to copy this. All right, so what is going to happen is, if we start with cell number 1, this shear flow, Q1, will be flowing in this wall, okay? Will be then in this wall here, flowing as well. Q1 is the same Q1. Don't remember last week I told you the shear flow in torsion is constant in the cell, right? It will flow then in this wall as well, Q1, and then it will go up in this cell, also Q1, okay? It will go up in this wall, I mean this wall, Q1. Now, if you go to cell number 2, this one in the middle, you will have a shear flow Q2 in that cell, right? So this shear flow Q2 will be flowing. So maybe I can change color of this Q2. Let me make it red. This shear flow Q2 will be in this direction. So you can see it's anti-clockwise in the cell, right? So it needs to go downwards in this wall, Q2. Then it goes this way in this direction, Q2. Then it goes up in this wall, Q2. And then it goes. Okay, you see? And then we do the same for cell number 3. Now maybe we can use the green color for this guy. Let's make it green. All right? And then we will have what? Q3 in this wall. Q3 and Q3, right? You see? You are going to see why I am doing this. Why I am doing this. You are going to see very soon. Now, what we need to have now is we need to use this equation for the gradient of twist. So the gradient of twist for cell number 1 will need to be equal to the gradient of twist for cell number 2. Okay? And we will have another equation that is going to tell us that the gradient of twist of cell number 2 will have to be equal to the gradient of twist of cell number 3. Okay? So that if cell 1 rotates by 1, cell 2 rotates by 1 as well, cell 3 rotates by 1 as well. And the entire cross-section rotates by the same amount. That is what these two equations are telling me. Okay? Are enforcing. These two equations you have here are enforcing that these 3 cells rotate by the same amount. And that this situation never happens. This situation here never happens. Okay? So that's what I am imposing, that's what I am enforcing in these two equations here. Alright? A very important point. And why am I doing this? Because don't forget, we are trying to calculate the shear flows Q1. So the shear flows Q1, Q2, and Q3, that's what we are looking for. We don't know how much they are. That's what we are looking for. So there are basically three unknowns in our problem. So far I have 2 equations. They are here, 2 equations, right? I need a third equation to get these 3 shear flows. Where am I going to get this third equation? Well, I'm going to get this third equation from the torque equation. The torque of the entire cross-section, which is given 10 power 4, needs to be equal to the summation of Q to AQ of each cell. Or if you want, maybe it's better to write for this example, to write something like this. Is equal to 2 times A1 Q1 plus 2 times A2 Q2 plus 2 times A3 Q3. This equation 2AQ is the equation we derived last week, remember? That relates the torque with the shear flow. In fact, I can be more accurate in my... So this is A2, like this. This is more correct, okay? Which is something that, look, we know the torque, we can calculate the area of cell 1, area of cell 2, area of cell 3. It's quite easy. You have all dimensions there. So we can easily also define this equation, right? This equation is again the same equation. The torque, external torque is equal to, needs to be in balance with the torque generated by internal shear flows, okay? They need to be in balance, in equilibrium, right? So then we have 3 equations for 3 unknowns, and this is the key to solve this problem quite easily. So let's work these 3 equations in the next slide. So maybe I copy this again. I will need this figure. So my proposal is we finish this example now, we do a break, and then on the second half we start the structural idealization, okay? Which is something very nice. You are going to enjoy. Well, there are things you can enjoy more, but at least in the middle of all of this is something you will enjoy more. That's what I mean. The reason is because it will make your life much easier, okay? That's why we tend to enjoy these kind of things. All right, so let's work the gradient of twist for cell 1. Let's change color. So we need to use this equation 1 over 2 AG times the contour integral. Okay? The equation we derived today. Yeah, so let's work. So this is for cell 1 only, so we are going to focus on this cell 1. And we need to work this, well, we can, so 2 times the area is quite easy. Area of cell 1 is 0.2 times 0.2. You all agree? This is the area. You all agree with me or not?
We don't
Yeah.
count for the thickness, so what are internal to the dimensions?
Yeah, I just deleted, but I deleted the equation, right? I had just before. Okay, let me see if I can recover that equation. Yeah, thickness is here.
Oh,
Okay? Redo is not working. Okay, so 2 times, now the area is 0.2 times 0.2, agree? So it's the area of this cell 1. Now, the model of rigidity, I'm going to leave it G. Why? Because when you write this, the G will cancel, right? So we don't need to replace. We can save some time. Sometimes we tend to be a bit lazy, right? So G over there. Now I'm going to work the contour integral. So I'm going to run over the walls of this cell 1. So let's start with this wall here. This wall here, okay? Let's start with this wall. So I need to have the shear flow in that wall is Q1. So I'm going to write here Q1 is the shear flow. I need to multiply this shear flow by the length of the wall, which is 0.2. And I need to divide by the thickness, okay? So the thickness is 0.001, right? Or 1 over 10 power 3. Agree?
Sir,
Yes?
can you explain why you multiplied by 0.2?
Yeah, because the equation for the gradient is this one, right? So when you do the contour integral, this S variable is a variable running through the walls, right? That's why you need to multiply by the length of the wall, okay? Okay, so now we need to move to the next wall, which is this one, here at the bottom. So I need to add the contribution of this wall. Again, the shear flow in this wall is again Q1. The length of this wall is also 0.2. And the thickness of this wall is also 0.001. Okay? Now I need to move to this wall, and now this wall is a bit critical. You see this wall here? So let's do the analysis for this wall. So I'm going to continue here, okay? I'm going to continue here below. So in that wall, there are 2 shear flows there. We have Q1 going upwards, and then we have Q2 going downwards. So what we need to have in that wall is the balance or the summation of these 2 shear flows. So what I will have in this wall is going to be Q1 minus Q2. Why is it Q1 minus Q2 and not Q2 minus Q1? Because in cell 1, we are adopting the positive anti-clockwise movement for the shear flow, right? And Q1 is in this anti-clockwise direction, and Q2 is opposite with this anti-clockwise. So Q2 should be affected by this minus, okay? We need to multiply this by the length of this wall, which is 0.2, and divide by the thickness, which is 0.004 meters. Right? Or 4 over 10 power 3. And the last wall we need to consider is this wall here on the top. we need to add this contribution, which is the shear flow is Q1, the length is 0.2, the thickness is again 0.001. And that's it. This is my contour integral for that cell number 1. And if we do these calculations, we get the gradient of twist. Of course, we cannot do it yet because we still don't know the shear flows Q1 and Q2. So we need to continue the analysis and move to cell number 2. Okay? So let's move to cell number 2. Maybe we can speed up now a little bit. For cell number 2. Okay, cell number 2 now, this one in red. We are going to calculate theta over L. 1 over 2 times the area of cell number 2, which is 0.4 times 0.2 times the model of rigidity. Now the contour integral. Let's start with this wall here in the bottom. We have the shear flow, which is Q2, times the length, which is 0.4, times the thickness, which is 0.002. Right, see? Now we move to this wall here. Again, this wall has 2 shear flows there. We have Q2 and we have Q3. So we need to do the balance of these 2. Basically, it's Q2 minus Q3. We need to multiply by the length, which is 0.2, divided by the thickness, which is 0.004. We move now to this wall here on the top. Okay? So shear flow is Q2 in that wall, the length is 0.4, the thickness is 0.002. And we finish this cell with this wall now. Now what do you think I should have? Q2 minus Q1 or Q1 minus Q2? Q2 minus Q1, yes, very good. So in this wall now I will need to have Q2 minus Q1 times 0.2, which is the length of the wall, over the thickness, which is 0.004. Done. For cell number 2. Right? As you can see, in these 2 equations we derived for cell number 1 and cell number 2, the unknowns we will have at the end are Q1, Q2, and Q3 after doing now the analysis for cell number 3. Okay, so let's do quickly the analysis for cell number 3. Copy, paste. Now focus on this cell number 3. We will get theta over L equal to 1 over 2 times the area, 0.2 times 0.2 times the model of rigidity. Did I put model? Yeah. Contour integral now. We can start with this wall here in the bottom, for example. Q3 times 0.2 over the thickness, which is 0.001. Now moving to this wall. Okay. We have Q3 times 0.2 as well. The thickness of this wall is again 0.001. This wall here in the top, we have Q3, 0.2, the thickness is 0.001. And the last one we have is this wall here, should be Q3 minus Q2, right? The length is 0.2 and the thickness is 0.004. Okay? In fact, let me move this guy here below so that I can put everything. Yeah. Good. Now, what do we have to do now? We have to write this equation, saying that cell 1 and cell 2 will rotate by the same amount. So if I do that, I need to get this equation. Let me just copy. So this is the gradient of twist for cell number 1. And I need to get the gradient of twist for cell number 2, this one here. Right? And then what I need to say is that these two gradients of twist, they need to be equal. Right? So I'm going to basically say that this and this, they need to be equal. Equal, right? And if I do that, look, this G cancels, goes away, right? But anyway, we have here one equation. The other equation you will get is this second equation here. The twist angle for cell number 2 and cell number 3, they also need to be the same, right? So if you do that way, you will get what? So this is the twist angle for cell number 2, this one in red. I can just copy and paste and put it here. Now I need the twist angle for cell number 3, which is this one here in green, right? Two equations, right? So this G, as you can see, the G also cancels the modular rigidity. You might have situations where this G is different. For example, I'm thinking in an aircraft, you might have some cells with metal, right? And some cells with composite materials. The G might be very different. So in that case, this G does not cancel, right? When you do this, you need to consider the G over there, okay? The third equation, we can do the third equation. So let me just move all of this stuff to see if everything fits in one slide. Good, I can move this up also a little bit. The third equation we need to have is this one here for the torque. Right? Which we can work this equation very easily now. So these areas are very easy to calculate. So I'm going to delete anyway. I need space. So 2 times the area of cell number 1. So the area of cell number 1 is this area. Is 0.2 times 0.2, right? So this is the area of cell number 1. I need to multiply this by the shear flow Q1, which is the shear flow at cell number 1. So this is the contribution for the torque from cell 1. Contribution for the torque from cell 2 is 2 times the area of cell number 2, which is this area. 0.4 times 0.2. Right? 0.4 times 0.2 times the shear flow in that area cell, which is Q2. So this is A2, right? And the contribution from the third cell is the area is 0.2 times 0.2, and the shear flow is Q3. Right? And this torque was given is 10 power 4, so I can replace this torque by 10 power 4. 10 power 4 here. 3 equations for 3 unknowns, which are the shear flows, Q1, Q2, Q3. Problem C. Okay? Right? So once you have the shear flows, so don't forget, I asked in the question to calculate the gradient of twist of the entire cross-section. What you can do is, once you have the shear flows, you can use any of these. You can use the equation for the gradient of twist of cell 1, you can use the equation for the gradient of twist for cell 2, or you can use the gradient of twist for cell number 3. Why? Because we enforced these 3 to be equal, remember? So if you use any of these, if you use the gradient of twist for any of these 3 cells, it should give you the same answer at the end for the gradient of twist, okay? So once you solve the system of equations for Q1, Q2, Q3, you just go back to these equations, you replace. In this case, you need to replace Q3 and Q2, and then you get the gradient of twist, which is the gradient of twist of the entire cross-section. Because we enforce it, theta 1 equal to theta 2 equal to theta 3. So they need to be equal, right? Okay? Let's do a break now. 5 minutes? 7 minutes. Or less. All right, so let's do a little bit more. Maybe what I will start this structural idealization, which is an important subject for aircraft structures. So I will start that today, and we continue next week. So, but at least I want today to discuss with you how we can calculate, like I said at the beginning, how we can calculate the area of this, what we call these booms. All right, so, aircraft structures, they can be very complex. What you have here in this figure at the top, well, you have the skin, okay, which basically the skin, for example, if you think on a wing, right, the skin gives the shape of the airfoil, right, for aerodynamics, to get the lift and drag. But if you have only the skin, with such a huge force, which is the lift and the drag on the wing, if you have only the skin, what is going to happen is the skin, don't forget, we try always to minimize the weight in aircraft, right? So we try to get the thinnest skin that we can get for the wing. But if we have only the skin with nothing else, because the skin is very thin, what is going to happen is when you put the lift on the wing, so the wing will bend, right? And then, in bending, you are going to have, you have the neutral axis. Below, you can have tensile stresses, right? And above, you can have compressive stresses or vice versa, right? Remember that from bending? So, if you think on this skin, very thin, under the effect of compressive stresses, if you don't have anything else there, the skin will buckle, right? Right? Agree with me? So it means we cannot have only the skin. So what do we need to have is, well, we need to have spars. So this is a cross section, right? So these two spars. So if you, for example, if you put the wing like this, right? So these spars, they run along the longitudinal direction of the wing, right? They can be, for example, I-shaped beams, or C-shaped beams, or U-shaped beams, whatever. So when you do this thing, for example, we are reducing the chances of the skin buckling. Why? Because if you don't have the spars, if you only have the skin, imagine, for example, this skin here on the top of your wing, right? If you have only this skin, so you can treat this skin like a plate under the action of compressive forces, right? So the buckling load, so this the critical load for buckling here depends on the dimensions of this plate. This dimension in this direction, and this dimension in this direction as well. Okay? So when you put the spars here, and when you, of course, join the spars. Sorry, let me erase this. When you put the spars here, and when you join the spars to the skin, what you are doing, in fact, for example, you are using now a plate with a dimension in this direction, which is much smaller than this dimension here, right? So you are reducing the chances of buckling of the plate. But sometimes this is not enough. We need to have something more, because even that way the buckling can happen, for example. So it means we need to have, you see these stiffeners here, we call stringers. We need also to have, for example, a stiffener here. So this stiffener will run also in the longitudinal direction. So I am reducing even more this dimension of this plate so that it does not buckle, for example, right? You see what I mean? So we have a lot of these components inside the wing that we call the wing box. That they are spars. So imagine, for example, I have a I-shaped spar, Z stringers. I can have another Z stringer here, for example. Another Z stringer here at the bottom skin. I can have more Z stringers here, and so on, right? Instead of 2 spars, I can have 3 spars. I can have here a C-shaped spar, for example, something like that. So the wing box, which is this cross-section, what is everything inside cross-section, can have a lot. And if you look at the real wing box, you for sure can find something on the internet. You can see how complex these structures are inside the wing, right? Very, very complex. So everything we have been discussing so far, if you think on transverse shear, bending, torsion, if we are going to do all this analysis we did, look, in the first hour, we did for a multicellular rectangular cross-section, very simple geometry, right? Imagine doing that in this very complex geometry. It's very difficult, right? Very, very difficult. So we need to find a way of building a model that is, we call idealized model. So we are going to make a lot of assumptions, but we need to find a way to make a model that is much simpler than the original model, so that we can do some analysis in the design of the wing, for example, right? You know, when you are designing, imagine you work, for example, for Airbus or Boeing or whatever, and you are given the task to make a wing for some aircraft, okay? Design. First, you are not going to work alone. You are going to work in a team, so don't be worried. But during this design process, you need to do a lot of iterations, right? So you come up with your first design, then you do this stress analysis, and then you find out, okay, the stress here is too high, the twist angle is too high, so we need to change the design, so we need to maybe put one more spar, then you need to redo the analysis again, and then you find, oh, this new spar is still not good enough, it's buckling, this part of the skin is buckling, so we need to reinforce here with a stringer, for example, and you calculate everything. So during this design process, you can calculate this many times. So what you want to do, you know, the engineers working on this, they are expensive, right? 1 hour work costs a lot of money. So you want to do, especially in these initial iterations of the design process, you want to do a quick analysis to see if you have the right number of spars, if you have, you know, the right number of stringers, if the dimensions of your spar are the right dimensions. So that is where these idealized models that I'm going to show you how you can get, they are really important for these initial iterations of the design process, okay? So you can have an idea, you can refine your design, and then when you are confident that your design is good, then you need to go, for example, FEA analysis. You go to Abacus, for example. Yeah, by the way, you had FEA already? Finite element method, numerical modeling. So you are going to learn, there is a model, you are going to learn that. So once you are confident of the design of your wing, you go to a FEA package, a finite element software package. You model the entire wing in full detail. Okay, in that case, just to validate your initial estimations on the idealized model, all right? And also on top of that, once your FEA model gives you the results, the good results, then you do, for the Airbus, they do also experimental testing. They put the full wing in a huge rib, and they put the full loading. You can see that on YouTube. I think maybe next week I can bring a movie just to make a different lecture, but I can show you that test being done on a wing, right? So you have to do all this kind of testing. But this idealized structures, this is in practice being done, especially on the initial iterations of the design process. Okay. All right. So we want to move from this to this model to this model. So the first, we are going to make assumptions on the geometry and on the stress installed on each of these components. Regarding geometry, in the idealized structure, we're going to have a skin that we are going to assume 0 thickness. This is an idealization, okay? You might be thinking, 0 thickness, what is that? This is an idealization, okay? Don't forget that. And we are going to assume these cylinders that you have here with circular cross-section, always circular cross-section. And so this is and our geometry is going to be like this, nothing more than this in the idealized structure. A skin and these cylinders which we call booms, okay? With circular cross-sections. Now, we also need to do a simplification on the stress. For example, the skin in the real structure will carry direct and shear stresses. Direct stresses from bending, shear stresses from transverse shear and torsion. In the idealized structure, the skin will only carry shear stresses. Okay? But you might be thinking, okay, but the wing is also in bending. Bending, you know that we have direct stresses from bending. Who is carrying the direct stresses? Well, that's why we have the booms here. The booms, they carry these direct stresses, sigma. Okay? So it's these two simplifications in geometry and in the stress states that will bring a huge difference on this analysis. Okay? The first thing, before we start doing the analysis on these idealized structures, the first thing we need to know is the area of these booms. These booms here, we need to know what is the area of these booms in the idealized structure so that these two models are equivalent. They are equivalent, right? So that is the main thing we need to do. And I'm going to focus the remaining of the lectures today on how you can get this boom area. All right? And for that, I need a figure that I have here at the beginning. I need this figure here. Okay? So what you have here on the top is the skin, basically. Is the original or the full effective cross-section. So I am assuming that this skin is in bending. Okay? So if you have, for example, imagine you have this is neutral axis. Imagine I'm taking this skin here, for example. Okay? And then, if you have a bending moment, right? This skin here, the direct stress is in this skin, so I can put like this. The direct stress is in this skin. They will come from this equation, from bending, right? Agree with me? Direct stress from bending is equal to the bending moment, M. times the distance to neutral axis. So this y is the distance to neutral axis, is this y, right? And this I is the second moment of area of the entire cross-section, okay? This comes from bending. Yeah, so we are going to assume this. Don't forget, we are trying to find the area of these booms that you see here. So, and I'm going to build an idealized model where I'm going to have one boom, this one, boom 1, and boom 2. Okay? So as you can see, I'm going to assume 0 thickness for my skin. And I have this idealized model with, for this plate element, with 2 booms, B1 and B2. And I'm going to assume as well that at this boom 1, I will have installed this stress sigma 1. Is here. Okay? And in boom 2, I will have installed this stress sigma 2. Right? Okay, so I'm going to find the area of these booms from this model that you see there. This is a model. What do I mean with this, with a model? What I mean is that if you have the real structure on one side and if you have the idealized structure on the other side, you are not going to get exactly the same results for these two structures, because we made a lot of assumptions, simplifications, right? But I'm going to show you that you are going to have very accurate approximation. Okay? That's my goal. Not today. I'm not going to show you that today, but maybe next week I'm going to prove you that. So we are going to build this based on this model. And based on what? So if I want to make these two models equivalent, or as accurate, or as similar as possible, what I'm going to use is, I'm going to use again the equilibrium. So I'm going to say the summation of moments about point 2, or about boom number 2. So what I'm going to do is, I'm going to use this point, and I'm going to calculate summation of moments about this point. Then I go to the idealized model, I take the same point, and I'm going to calculate summation of moments about that same point for the idealized model. And then I'm going to say, okay, if I want to build the model that is equivalent to the real one, I'm going to say these two moments, they need to be equal. Right? If these two moments are equal, basically I'm saying, okay, in terms of the moments they are producing, the moment is the same. The real structure and the idealized structure are producing the same moment about point 2. This is a kind of equilibrium, maintaining the equilibrium, a kind of, okay? So that's what we're going to do. I'm going to calculate the moments produced by this real structure with this loading here, these direct stresses, about point number 2. And in order to do that, I'm going to simply to do this. I'm going to divide these distributed loads into a rectangular one, this one in green, and a triangular one, this one in red. This is where, I think we did this in year 1, right? Distributed loads, rectangular, distributed loads, triangular, distributed loads. So, let's start with the contribution for the moment produced by this green distributed load, this rectangular distributed load, right? So remember that I told you that for this green, I can replace this distributed load with a concentrated force located at the centroid of the rectangle. So don't forget this, the height of this distributed load is sigma 2, is a stress, is not a force. So I need to convert this into a force, right? So I will have what? This force is going to be sigma 2 times the area. Which area is that? Is this area here. of this. Are you seeing? And if I multiply sigma 2 by this area, I will get a force at the end. So that area okay, so that area is this B times the thickness. You agree? T? Okay? So this is really a force. And then I can say now that the contribution of this force to the moment is going to be, well, the force is sigma 2 pt. This is the force, right? I can write like this. Now, in order to have a moment, I need to multiply this force by this length, right? Agree? Which is B over 2, right? And then this is the moment produced by this rectangular distributed load about 0.2. Okay? Now, I need to add the contribution of this triangular, the one in red. So let's focus now on this triangular. So again, we will need to have a concentrated force on the centroid of this triangle. So the centroid, this point here, so this distance from here to here, which we are going to need for the moment, is going to be 2/3 of B. You agree with me? Right? Now this force, so I need to get the area of this triangle. So I need to get this height, which is sigma 1 minus sigma 2. Agree? So sigma 1 minus sigma 2 is this height. So I need to multiply by B and divide by 2. So this is the area of the triangle. But this will give me what? This will give me a force per unit length. So in order to have the force, I need to multiply this now by the thickness, T. So I have the total force. Okay? Now we are in good condition to get the moment produced by this triangular distributed load, about 0.2. And that moment is going to be equal to the force, which is sigma 1 minus sigma 2 times bt over 2. So this is the force. And I need to multiply this by 2/3 of B. Then I have the moment. I have the contribution for the moment of this triangular load, right? And then I need to do the same for the idealized structure. Okay? Which is much easier. Because look, if I calculate the moments about this point, about this boom number 2, sigma 2 does not produce any moment about boom 2. It's passing on the boom 2. I only need to add the contribution of this sigma 1 at boom 1. And that contribution is quite simple. The force, so sigma 1 is a stress. So sigma 1 is a stress, isn't it? In order to have the force, I need to multiply the stress by the area. Which area? Well, it's the area of the cross-section of the boom, which is B1. Okay? That area is this B1. So if I do this, this is a force. But I want to have the moment, so I need to multiply now by this distance, which is B. And then I get the moment. Right? Yeah, and then that's my moment for the idealized structure. Yes.
Sorry, is the boom just the, you said just the face, not the cylinder itself?
Yeah, the boom is the entire cylinder, but we are doing the analysis for the cross section, right?
I see.
So this stress is applied on the circular cross section of the cylinder, right? So the area you need to multiply the stress needs to be the area of that circle, which I'm saying is B1. Right, the only thing we need to do now is, what is this? What is this guy doing here? Right. What I need to do now, I need to make these two equations equal, right? So let's do that. So what I'm going to do is, maybe I can continue like this. I can do something like this. Let's see. If I make these two equations equal, I will have something like this. Maybe I think I will not have space there. So I will continue here in the bottom, okay? So I will have, from this first equation, I will have sigma 2 bt times b over 2 plus sigma 1 minus sigma 2 bt times 2/3 b. So this is for the real structure. Now I need to say this is going to be equal to the moment at the same point for the idealized structure. So this needs to be equal to sigma 1 b1 times b. Right? This guy cancel. What else can we simplify? Well, let me see. I can multiply everything by 2 eventually. Why am I doing that? Okay, so let's try to organize these terms. So let's see. Yeah, so I will have here okay, I will have sigma 2 times bt 1 over 2 minus one over 3. You agree? And then I have plus sigma 1 bt over 3 equal to sigma 1 b1. Is this correct or not? I usually have mistakes here. I don't know why. So let's check this carefully. Sigma 2 bt, I have 1 over 2, correct. So minus, if sigma 2 bt, 2 cancel with this 2 over 3. Seems okay. Now plus sigma 1, 2 cancels with this 2, bt over 3. Looks okay to me. Now what can we do? We can, we can do sigma 2 bt. So here I will have 3 over 6 minus 2 over 6 plus 2 sigma 1 bt over 6. Right? Then I can simplify this a bit more. So I will have sigma 2 bt over 6 plus 2 sigma 1 bt over 6 equal to sigma 1 b1. Almost there. So I'm going to copy this equation and move to another slide. Okay, let's continue from here. Now, I'm going to divide everything by sigma 1. So I will have what? Yeah, whoops. Yeah, I will have sigma 2 over sigma 1 times bt over 6 plus 2bt over 6 equal to B1. Don't forget we are looking for the area of the boom, so that's why I am isolating B1 on the right hand side. We are almost there. I can now say this, I can say B1 is going to be equal to BT over 6, and now I will have what? I will have here 2 plus sigma 2 over sigma 1. And this is the final expression. Let me just confirm. Yes. Oops. Yes, correct. So this equation here gives me what? Don't forget what is our main target, our goal. This equation gives me the area of this boom in my idealized cross section. And you are going to see how easy this is going to be. Why? You might be thinking, okay, B is fine, we have B, right? Is this dimension here? We have this, is given. T is the thickness of the real skin, is also given. We also know this. But the problem is, what about sigma 2 and sigma 1? This is not given. How can we get this sigma 2 and sigma 1? Well, don't forget one important thing, which is, imagine, for example, I give you this. Let's start with a simple one. Imagine I give you this, okay, this plate. Here is the neutral axis, okay? So this is my point 1, my point 2. I want to build an idealized model. So basically I want to build an idealized model like this. Boom, B1, skin, boom, B2. Here is neutral axis. I want to build an idealized model like this. So I want to calculate this area B1. So I need to use this equation here, okay? Now, I know that these stresses, sigma 2 and sigma 1, they will be, so here I will have sigma 1, here I will have sigma 2. Right? So like the stresses we had here in our original plate. But I know that I built my idealized model, this model, by saying that these stresses, sigma 1 and sigma 2, this triangular and rectangular distribution for the stress, they come from bending, isn't it? I said that. It comes from the bending of the cross-section. So I need to calculate these stresses here in this equation, sigma 2 and sigma 1, also from bending. Right? Because I built my model based on the bending. And it's quite easy for here, this sigma 1 is going to be what? The bending moment times the distance to the neutral axis of this point 1, which is this distance, over the second moment of area of the entire cross-section. And this sigma 2, the stress in this point, is going also to be given by the bending moment times the distance y2, which is this distance here, over the second moment of area. So if I do now this ratio, sigma 2 over sigma 1, I will get what? Bending moment, distance to neutral axis of point 2 over the second moment of area. Sigma 1 is bending moment, distance to the neutral axis of point 1 over the second moment of area. The good news is that the bending moment cancel. Second moment of area cancel, so I end up having y2 over y1. Which is amazing. Why? Because y2 over y1 is y2 and y1 are the distance of these points 1 and 2 to the neutral axis, which we also know is given. If I ask you, for example, get make a idealized structure for this plate. I need to give you the configuration of this plate, right? The dimensions, the distance to neutral axis. That is given in the question, right? So you know that. So we have everything for this equation here. We have everything to calculate the area of boom 1. What about the area of boom 2? Very easy. You can do the same analysis we did by calculating the moments about point 1 now. But we are not going to do that here. It's quite easy. You just need to flip this sigma 1, sigma 2. So this is going to be Bt over 6, 2 plus, now you have sigma 1 over sigma 2. You just flip now this ratio, right? And then that's it. Right? So we need to finish here because it's time to finish. But next week we will continue from this point, okay? All right? See you next week then.